So my name is Nicolai Josuttis. I'm writing books, and it's all my fault because I have been in standardization of C++ since the first standard, so 25 years ago. And I want to talk to you about C++ 17. C++ 17 is now 1 year old, or to some extent even more. And we make more and more experience about the problems we get. Yes, there are problems. Experiences, challenges, what the managers say. And that's my talk about the next minutes. For some reason, my presenter is not working, so I have to walk back and forth. Okay, as you probably, who has programmed in C++ 17 already? Oh, you want to all challenge me. Okay, that's good. So maybe you find, you hear other problems. Maybe you see the problems I saw. And so let's wrap it up. And if you have something more for me, please come to me and tell me. Just one statement before we go into details. C++ is community-driven. That means we have no chief architect. That means there is no one consistent design by one consistent person, which is not always the case if you have one chief architect at all. But we have about 150 different contributors to C++ currently, and they all make suggestions, have different ideas, have different contexts, have different ways to program, have different style, different experience, different age, different platforms. So that's our biggest problem. We are, to some extent, victims of our own success because this number has raised significantly since C++ 11. So it's at least something we did right. And we meet 3 times a year, next week in Hawaii, to work there. And then we come together and just people propose a change, and then we accept or reject, or we suggest to modify. Sometimes we are not aware of the consequences. Often we are. So just as an explanation, in case you're wondering why is this all maybe not worked out or looking different or not homogeneous, yes, that's the way it is if you standard by a community instead of a chief designer. And if you complain, I come back to you and say it's all your fault because you haven't been there. Okay? Good, just kidding. Hey, do you laugh here in UK? Yes. Yeah? Good, that helps. I'm German, sorry, we are the dry guys. Okay, so just one additional hint. When we standardize, we are working in different working groups. We have people working on the core language. We have people working on the library. We have special groups like for concurrency or tooling or machine learning or whatsoever. And then finally, we vote on everything. I would assume that nobody who votes on the last day understands what he votes about everything they vote. So we have to trust each other to some extent. And we make mistakes. Good. That's for the explanation. And I have to start with the first topic. The first topic is about initialization. Timo will give a talk today about initialization. So I just make it brief because I just want to point out that I use my style of initialization. So we have a mess in C++, and the mess is that we started with initialization the way C did. Then we introduced the way C++ does with parentheses. Then we introduced uniform initialization with curly braces. And the question is, what should we use? To some extent, brace initialization should have solved the problems of having different ways to initialize. Well, because we are backward compatible, we still raise the chaos. And the question is, which style should we use? And you will see in my slides, I'm now a total fan of uniform initialization. And why? The first thing, it's better. It detects bugs which are not there. For example, if you initialize an unsigned with a maybe negative value or with a value too high, then it works the way people read code. So if you have a vector of 2 integer values, you have 2 integer elements, surprisingly to some people, who come from old C++. Then you have, with auto, you have everything the way it works. So auto A1 is initialized by an int 42. We come to that in a moment. In C++17, we are now also allowed to initialize enum values only with integral. When we pass an integral value, the only syntax that is okay is to use curly braces. We can use it to initialize aggregates, now even with inherited aggregates. And you can always make sure values, there are values in the object. And there are some corner cases like here, where you have a hash object created with curly braces, and then using it as a function with parentheses, and you can see that difference, which, for example, also helps here when you initialize a vector of int, initializing by all the elements reads from an input iterator, so from the standard input. With parentheses, this would declare a function instead of taking the elements from standard in to read all the elements. So by default, this works fine. Use uniform direct initialization. We still have a few flaws that will be fixed in C++20, but these are very, very rare corner cases. But there's one thing, my first trap, which is if I declare something with auto and I use curly braces but an equal sign instead, then we run into a problem. And now the font size of the slides will improve a little bit. So if you, by the way, could somebody turn off this light, because this goes to the slide, and I think they are a lot better to read if you turn that off. Somebody here from the? Yeah, okay. Good. So, so the problem, we made a mistake in C++11. Oh yeah, that's one. When we use auto and initialization, curly braces to initialize an object, this was, yes, wonderful. We said this initializes an STD initializer list instead of an int. Everybody would read the third line as initializing an int. And we fixed that as a defect formally in C++17, but you will find this fix even in old C++ modes if you switch to the right compiler version. So in Visual Studio 15, GCC 5, or Clang 3.8, this is fixed even in C++11 mode. And there we have a fix saying that now if you take auto and curly braces, this initializes an int. And if you use multiple values, this is an error now. Before this was an initializer list of int. There is something in our world that sometimes is a problem. That's compromises. So there came the people who said, but if I write generic code, my generic code sometimes needs an initializer list, so how can I create it? And the compromise was, and this was one of the worst decisions we made with C++17, the compromise was, if you use an equal sign, this is still an initializer list. What? This means an equal sign in an initialization changes the type of the thing you initialize. That's a very, very, very bad design. I hope we will fix that sooner or later. But yes, this is the first trap you should know. So in any case, if you initialize things now, you might use it the old way using aggregate initialization, running over a loop of values, initializing an iterator with begin, or initializing the members of a class. And you see here, I don't use any curly braces at all. My new style will change that to the following, so that we use curly braces everywhere. And the most interesting thing where I discuss this with people and teams is the iterate over a range of values. So iterating from 0 to 32 with the third line. Do you feel comfortable with that line? For those who do not, use the old style. We are a multi-style language. But there's an interesting experience we had in a company where we teach that now for almost 1 year to a team of more than 200 programmers. We are getting used to it. We feel comfortable using curly braces. instead of an equal sign or parenthesis here. So some resistance of the curly brace initialization might be just caused because we are too old, too experienced. And that's, by the way, sometimes also the problem of the standard committee. They are only experts with many years of experience. Try to teach C++ to beginners, and you see what problem this causes. OK, so far, for the beginning, let's look and go through the different features we have in C++17 and where they create a problem. First of all, we have now if and switch with the ability that you can pass an expression to initialize something before you make your check or your switch. This is good if you see something like this. You have status to initialize, and then you want to check against the status and use it in the if expression. You can write that now as follows. So in the if statement, like in a for statement, before a semicolon, you can have an initialization at the beginning. And the scope of this initialization ends with the end of the if, which is the end of the else if available. And here's another example. That's an interesting example. If you need a lock guard to do something, you can write it that way now. So let's initialize a lock guard. So let's lock the mutex. And while the mutex is locked, we check whether a vector is empty. And if not, we print the first element. And the same is possible for switch. So what is the problem here? The problem, there are two problems actually people are running into now. The first thing is they think about, do we need a name for this lock guard here? So do we need a name for the object that does the lock? Well, you can make the name as a simple underscore. Some people prefer this style. Some people hate it. But you might say, oh, why not skipping the name at all? So just declaring in the initialization a lock guard, and then during the if, using it. The problem is a lifetime problem here, because this initialization locks a temporary object, but at the end of the initialization, the lock is gone, because the destructor of the element is called. So if you do that, you access your vector without having a lock on it. So don't do that. By the way, this is also true if you do the same trick with the for loop. This is nothing new, but for loops with lock guards in the initializations are pretty rare. And by the way, you no longer need here to pass the type of the mutex due to class template argument deduction, which we will discuss later. Here's another problem. The funny story about this is, this was a bug report, I think against Visual C++. They said, hey, your new if feature runs into a core dump. So what did they do? They had a nested if expression. So they said, first of all, we have to call something that returns a pointer, and then we use this pointer to some extent. And because people like new tools and want to try them out, they switched this code to this. So they said, let's initialize the object and then check it. So what's missing here? You see it all, I'm pretty sure. We have forgotten that in the first expression there were two if statements, so two conditions checked. So beside the initialization, the first if was also a check whether the initialization returned the null pointer. So there was missing an implicit if unary expression before we check the additional condition. So people, we were at least discussing a little bit time of this. Did we standardize something wrong? No, I don't think so. But you have to be aware, not just switching something that looks like an initialization into an if statement. Good. Aggregates. Before C++17, this class, struct_dv, or this struct, was not an aggregate. So it did follow the rules of classes, which means the objects of this class or of this type had an implicit default constructor, and you could create them with this implicit default constructor. So, which meant that you could create the objects without curly braces and with empty curly braces, and with curly braces you got the values initialized without not if they didn't have a default constructor like the string name. You couldn't pass multiple values in a way that you want to initialize both the parent elements and the derived elements, neither with nested curly braces nor without nested curly braces. To do something like that, you did have to provide a constructor taking the necessary arguments and pass them to the base class. This has changed. Since C++17, this is by rule an aggregate. An aggregate can now derive from another type. The other type might not be an aggregate. So there might be, for example, strings involved. So now the initialization with curly braces you see on the bottom is now valid, both with nested initialization, so with the inner curly braces you pass 2 elements to the base class, and then the false to your derived class, to your member of the derived class, and you can, by the rules which were already there in C, skip the inner braces, and then they fill up as they find elements from top to bottom and from in to out. What is the problem with that? Well, look at this. You have programmed this. You have a data structure, and in this data structure you have, for whatever reason, said, I can't create this with a default constructor. Now, before this was an aggregate, that meant this should not work to create something. But with C++17, this is an aggregate now, and see what you can do. Using a default constructor, not passing any elements and no curly braces was an error and still is. But using empty curly braces was not an error. This did compile. When I tweeted this around, I think somebody answered that this is a what the fuck of C++ of the month. So yes, this did work, and this was code that was valid. When we found that, we immediately raised this issue for C++17, and this will be fixed in C++20. So in C++20, this will behave as, well, 19.999% of the programmers would assume that if you have a deleted constructor, this will mean that you can't create objects. By the way, we had some thoughts. We did fight about this change. There were people against this change. So they thought it's a good feature that CD1 is not possible, but CD2 is possible. And you know why? Because we could force users of aggregates to pass something to initialize, and if it's nothing. So we could force here initialization. But we discuss it, and it will be fixed as we want to use it. OK, heap memory allocation. You might have heard that heap memory allocation now supports alignment of data. So since C++11, you can say my structure is aligned so that the address of objects is at an address divisible by 32 without remainder. And you can even in the declaration say that val2 here is 64 bytes aligned. So what's wrong, or what's the problem here with C++17? Well, this in C++11 was only supported on the stack, not on the heap. So on the heap, this did not work. We had to invent something. And the biggest problem we needed was if we supply this feature on the heap, we need new overloads of operator new and delete. Because you can implement operator new and delete yourself, and to some extent you need a way to pass this 64 to the implementer of operator new and delete. And that was introduced in C++17. So we can now say on the heap, so with new, let's create an object of this type, initialize or not. And you know what? This will call a specific and a new operator, new and delete, which you can implement yourself. We have something like 20 different overloads of operator new now provided in the standard. Some of them are necessary, some of them are derived from the others. So what is the problem? So why do I tell you that if we talk about traps of C++, C++ 17? I thought when I document this feature, wait a minute. When I document this feature, so heap memory aligned allocation, this will take me 1 day in the book. It took me 1 week, and the chapter has more than 30 pages because there are some flaws and some issues even explaining the situation before C++ 17. And here's the biggest thing we have. You can, on a stack, say, beside the fact that my objects in general are 32-byte aligned, let's, in a special case, align them by 64 bytes, which you say, since C++ 11, the way you do that with val2 there, just writing in front aligned as 64. So how do you do the same on the heap? Well, you are passing an argument to operator new. So you're passing to new a new align val_t type, which is especially designed for that, and that's exactly what the new operator new takes as an argument, and say what your favorite alignment is. For example, here 64. By the way, if this 64 is your default alignment or less, the normal operator new will be called. Just your operator new will be called if this 64 is higher than the default alignment of your type. So what's the problem? The question is, how do I call delete? Because in heap memory pools, you can now say, if there's a specific alignment requested, I use a different pool of data for my heap memory allocation. So when I free it, when I delete it, I should free and delete it from the same different pool. So I should not go the normal way. And the point is, that means when you call delete, you have to pass this alignment request again, because it's not stored in the type. As you know, the types only are pointers to memory. So the delete needs an additional alignment argument to be perfectly portable. But we have a problem. We have no delete with a syntax saying, here is the argument for your delete. Or in other words, we have no placement delete. We only have placement new in the language. So what we really needed would be something like this, to say, when I call delete, I pass you that the object was aligned to 64 byte. That's not supported in the language. So that means you have to call the delete operator directly, not by calling just delete, by saying, I want to call the operation of the implemented operator delete, which you see here on the top. So you call the global operator delete with P1, and then as a second argument, you call the alignment. Okay, that might not be very nice, but maybe necessary, but that's not all. The problem is, you might not know whether objects of this type have their own operator delete or not. For strings, as requested here, we know they have no specific operator delete defined, so you know that you are safe if you call the global operator delete as here. If you have your own type, then you might not know whether this type has its own operator delete defined. So there are two options. Either you call the global operator delete as on the last line, or if it has its own implementation of operator delete, you need the syntax on the line above, which says I go to the types operator delete and call it. So as a caller of the delete, you have to know whether there's a specific operator delete for alignment design. And that's a problem for which we need placement delete. We don't have it yet, so you have to know more than necessary to deal with this feature. Okay. Good. Something totally different. Most operators have no evaluation order in C++. That means if part of the operations are side effects where you call something, you don't know when the things are called, except for operators and so 2 ampersands and or, and the comma operator where we guarantee to go from left to right to evaluate the expressions from left to right. So this was the example. Similar example was in Bjarne's C++ book, and this example turned out to be invalid for years, for centuries. And so people thought that this example prints out, it sometimes works if I believe. Assuming that first we replace the first 8 characters by nothing, then we find the word even and replace that 4 characters by sometimes, and so on. The problem was, this was not defined. Other outputs of this before C++17 could be this. Because there was no guarantee when the find expressions were evaluated. So it could be that we call s.find before we replace the first 8 characters by nothing, and then we would get a very different index where we replace 4 characters by sometimes. So this was code that accidentally, most of the time, worked correct, but only accidentally. And we have the same error, it's the same problem in a couple of other places. So here, for example, if you print out the result of the function called f, g, and h, people assume that f is called before g. That's a wrong assumption. It might be that g is called before f. And if there are side effects, this has an interesting effect. And the other example is this: print out incremented I and then decremented I. This also, it was not defined what was printed here. In fact, if you tried it out at different compilers, possible outputs were 1, 0, 0, 0, or 0, -1. We fixed that. So we have a new definition now for guaranteed evaluation order for some of the operands, not for all. So for the dot, for the left and right shift operator, because it's used in function calls, and also for function calls, it's guaranteed now that the left side, the left expression which defines which function is called, is evaluated before any argument I pass. The order of the argument evaluation is still undefined. So on the right side, A, B, and C might be evaluated in different order, but it's guaranteed that expr on the bottom here is evaluated before anything with A, B, and C if these are expressions. So it's guaranteed now that the example on top now gives the first lines in C++17 that this is guaranteed to call f before g, and this is guaranteed to print 1, 0 since C++17, which might change your existing behavior in your programs. Who did know this change? Oh, only a few. Why is this something you should look at? You might have test suites expecting some specific output, and suddenly your output is different when you compile with C++17. Here's an example we ran into in some project. It's a simplified version of that. Here I have a function printing an element of a vector. I pass the index and a prefix, or an optional prefix. So I print first the prefix, and then I call add, because I double check whether the index is valid. And this add call might throw an exception. So, and then here's some code that calls this function. This code intentionally forces the error, the exception, because it iterates from 0 to size, including size, using the old style without curly braces, by the way. This is an old slide. And the problem is, yeah, using the index, which is equal to the size of the collection, is of course wrong and should create and cause this exception. And the interesting thing is, in a couple of compilers, this creates the following output. Look at this very carefully. We print the elements, the first 4 elements, and then for the invalid index, we run into the output of print element, the output statement. And there, first add is called before we print out the prefix. So therefore, we don't print the prefix yet, so just add is called, which raises an exception, and we print out the exception. Because one other option of this is that first we print the prefix, and then we make the add call. So there were 2 different options what could be printed here, and a couple of compilers did do what the first output demonstrates, that would no longer be valid. So it is now guaranteed that the prefix is before we evaluate the add, and your output, and if you have a test suite or something like that, might change accordingly. Okay, that's just a simple case, but there are more corner cases like that. I don't think this makes invalid code suddenly valid, but if you have test suites like that and you are expecting specific output, the output might have changed here. Okay, so far language features. Let's talk about templates. We have a compile time if const extra. The compile time if is useful if you have different checks and not all the checks are valid in a template function or a function template. So look at this. We want to convert something we pass to as string to a string. And sometimes we have to call toString. Sometimes we just get a string, we return it back, and sometimes we call the constructor of string. And if you, for example, pass 42, so which is an int, calling the constructor, which is the last else statement here, would be just invalid code. The invalid code means that this will not compile. And so with the runtime if, this should not work, because with the runtime if, all the lines, all the statements have to be valid. So we switch to a compile time if, and with this compile time if, we can make sure that if you pass 42 and you want to convert it to as in, the last statement here, the last return statement, is not compiled at all and must not be valid code. Okay, so that's a good thing with compile time if. 2 things here to comment. First of all, if you are used just blindly that if return needs no else, don't do this here. Because if you do that here, you undiscard the last return statement. So you learned that return is good enough, because this must be a compile time else, otherwise this code always has to be valid. So it would no longer depend on whether the compile time conditions apply or not. There's another problem, though, here, which is more severe or more surprising to some people. So let's call a function foo, and at compile time we decide if this is an integral value and the value is greater than 0, I call myself recursively again. And a couple of people might assume now, let's wait. I don't think we need the else case at all in our program. So let's place a static assertion false. Let's place static assert false here. And suddenly, your code might no longer compile, even if you never use the else case. So even if you only call foo with integral types. So what is the problem? The problem behind this are sophisticated rule of template instantiation. Template instantiation is done in 2 phases. The first phase is, let's check whether the code is valid, without knowing how the template arguments are deduced or how they are specified. So without knowing what the type of T is. The rule is, without knowing what the type of T is, everything that does not depend on T has to be valid. And if you write static false, this does not depend on T. So this will lead to the effect that if you see this template definition, your compiler stops compiling and says, I have a compile time error. Even if foo is never called, this is the effect of this static assertion. The same is true if you have some undeclared function calls. This check, whether undeclared exists or not, is done at definition time. So when the template is seen, there must be a function undeclared, otherwise this function template will not compile, even if the else case is never used, even if it's not called. Only when calls and expressions depend on template arguments, they are delayed until instantiation time, so when we know what the type of T is. So beware of this static assert. A couple of people run into this and were very surprised about that. So in the static assert, you would have to write the same is integral check once again. Or the opposite, not is integral. By the way, if you're using Visual C++, this will work. So because Visual C++ has not correctly implemented the two-phase handling of templates. For those who will tomorrow attend my class, full-day class about modern C++ template programming, we will talk a little bit more about that. They know that. They've done that for years. They can't easily switch now to the correct behavior, so they have now a path to fix this. But this will not be a problem in Visual C++. So the assertion will not fail, and calling undeclared will not fail. You might be a little bit surprised if you then port this code to GCC and see a problem there. Good. Something else, class template argument deduction. So we have now in C++ a new feature where we say templates, class templates, no longer necessary need a specification of all template parameters. So you can say, instead of specifying that my complex takes 2 ints, so the class has to be a complex of int, you can let the compiler deduce that from your constructors. So it's enough to say, with the old or with the new syntax, to say, I pass to a complex 2 integral values, and that's it. Because according to the constructor, taking 2 ints, the compiler knows that for this class, template deduction works, and that the template parameter of this complex type is int. Which of course has to be, there can't be any contradiction, so if you pass an int and a float, or floating point values or double, the compiler has no clue what to do and will not compile here. Which is especially useful for lock guards, for example. You can skip now passing to lock guards the mutex type, because the mutex type is deduced from the constructor of the lock guard, where you pass the type of a mutex implicitly. Here's another interesting example I recently learned. So if you call sort now and you use one of the standard function objects, the standard function objects like std greater, usually in the past needed the element type. With C++ 11 we fixed that, no, it was 14 I think, that you only need empty angel brackets, but even the empty angel brackets are no longer necessary, because now according to the constructor, the implicit template argument void is deduced here, which works fine. So we can write this code now that way. Whether this is more readable or not, I'm not sure about that. But it's possible now. So that's a good moment where I want to see whether you are all awakened. So who has used class template argument deduction already in some code, or at least in some thought experience. So let's see whether you know everything right. So this is vector. This is a vector class definition. On top, you have all the constructors. So we can say now my vector, without specifying the element type, takes in curly braces 2 elements, 8 and 15, and then the compiler finds out which constructor is called. So which constructor is called here? The last one, taken an initializer list, because due to some language rules, this has the highest priority of those who might apply. And this will initialize a vector of int, so it will deduce because that the type t is int, because this is an initializer list of int. And that works. And what you always need is somewhere in the constructor a t, so your type of template argument you want to deduce. So if you have one element here, this will also work now. So you got it? Wonderful. Let's talk about some other things. What is the effect of this statement? Any suggestions? Eight element of value 15. That's correct. Why that? Because the initializer list constructor requires curly braces. When you don't use curly braces, this can't be passed to an initializer list constructor. No way. So only the others are possible, and the only one that fits, or the one that fits best, is the one taking a size element, size n, and then the value of t. Good. And if you pass just one element, what constructor is called here? So how do we decide, how do we deduce t here? The what? Default? But if we call the default constructor, how do we deduce type t? Well, the answer is this will not compile. Because we find no constructor, matching constructor, or the matching constructor we find is not able to deduce type of t. So the constructor that probably will be called is the third one, taking a size t element, but it could also be just an element to initialize a vector of int or so. In any case, the compiler doesn't find a constructor taking t. So how about this? 8 empty string literals. 8 zeros? Well, I would say if we take v3, 8 times an integer of 15, this should be 8 times a const character pointer. Did you say pointer? No. What is the type of the 2 double quotes? That's, yes, here it is. It's an array of 1 character, which contains a \0. And by the way, that's deduced. Yes, type t is deduced here as being an array of 1 constant character. And the reason is that the constructor takes t by reference. If it would take the argument by value, the type would decay to a const character pointer. But because the constructor, it's the fourth one from top, takes it by reference, t does not decay, so the type of t is const character 1, which does not compile, because internally in the vector, this type is used, t is used in a couple of places, and some of the places are not valid if this is an array. Okay, are we done yet? No, more surprises. STD set of string. Let's initialize a set of strings, and let's call the vector with curly braces, passing the begin and the end of this vector of strings. What is the effect? Which constructor is called? The one with the initializer list? All agree? But yes, she's right. Yes, the rule is curly braces, initializer list is valid. This is the best fit we have. So because we don't have a template here, non-template it hits template initialization. So yes, this is an initializer list. So this initializes a vector of set of string iterators. Okay? Which would not be the case if you explicitly, if you wouldn't use class template argument deduction and would say vector of std string, then it would initialize this by the elements of the set. So sometimes class template argument deduction is to some surprises. So what happens if we use parentheses instead? Then the initializer list constructor can't be it. And it's an error. Why is it an error? Can't deduce a type. Yeah, the constructor call is a vector constructor taking two input iterators, but we can't deduce type t from these input iterators. How come? There's no t in this constructor involved at all. So for that reason, in the standard, we have what we call deduction guides. We have a deduction guide helping the compiler here, saying, when you get a pair of iterators for initialization, please deduce t to be the value type of the iterators. That's part of the standard. So now, still with curly braces, we have the old behavior, but with parentheses, we deduce a vector of string here, and this will initialize the vector v7 by all the elements in the set. I would suggest that you use not class template argument deduction. I would suggest that you explicitly specify the element type in this case. Are we done? This is, by the way, the fully specified deduction guide. Are we done now? Well, what happens if I pass in curly braces two string literals of different size? Which constructor is called? The initializer list one, the last one still. Yeah, curly braces, same type. So, yeah, initializer list of t, this initializer list of t is passed by value. No, excuse me, because we have two different types here. They decay to type t, to a common type, which is const character star. So this works. This will initialize a vector having these two string literals, so const character star, not std string. And what happens if I use parentheses here? We don't have such a constructor. No, this is not an error. This will compile. Well, I should not say this is not an error, but I should say this compiles. This compiles. Which constructor is taken? The one with the two iterators. Yes, because the input iterator constructor takes the arguments by value. That means both string literals decay to const character star. Const character star is a valid iterator. So this has the interesting effect that we initialize the vector of character, because we are pointing to characters, and we initialize the vector with all the elements from the address of the high string literal to the address of the world string literal, wherever they are located in the program. At best, you get a caught up. Okay, so yeah, we have some interesting effect. Be careful with class template argument deduction. It works fine in many cases, but not in all. And we have seen these bugs already in production code or as compiler feedback, as for feedback to the compiler vendors. So far, let's talk about the library. Okay, half an hour left. We have new vocabulary types, optional, variant, and any. Let me talk about one of them, which is the most interesting. Well, the most interesting is probably variant, because it introduces a new way of polymorphism, but it works pretty robust and pretty well, unless I don't know a problem I should know yet. I don't know yet a problem I should know. So let's talk about optional. Optional, it is interesting. It's just saying I have an optional object. So that means if I have value semantics, so my object always has a value, I can say, no, there is no value. And by declaring it as an optional string, you might know also this type from Boost. So what's wrong, or what's the problem with this data type? A couple of things are, well, something you should know. First of all, you can compare optionals directly to values of the underlying value type. So that means you can say, if my optional has an int, I can compare this optional int directly to 42. That's a feature, that's not a bug, but it leads to some surprises. Look at this. I can check whether an optional bool is less than false. And this might be true, because if there is no value, the rule is any optional value that has no value, so any optional state that has no value is less than any other value, which means we can put optionals in a set, or we can sort them, and at the beginning and front, or the minimum values are always the ones that have no value. No value is less than any value. That's the rule for optional. So that has this effect. You can write this thing. Or you can also compare against an unsigned value and checking whether you have a value less than an unsigned 0. OK? And here we have more funny stuff. If you have an optional bool initialized with false, there's a difference between checking is there no optional value or is the optional value false. Yeah, so beware. By the way, the reason we have optional in C++17 and not in C++14 is that we couldn't agree on how to deal with this situation. And we thought about having some specializations for optional bool, but at the end we thought this is not worth it. I mean, people should know this trap, and besides the fact that an optional bool is some interesting object. So you have a 3-state object. Maybe you should use something different there. But sometimes it makes sense, of course. And the same is true if you have an integer pointer, a raw pointer, which is optional. There's a difference between applying the not operator, which means is there a value, and checking against the null pointer. So these two codes are different. Which is especially interesting if you have these lines in generic code. Yeah? So there's a difference between these two things. And suddenly you pass an optional to your template, and suddenly, yeah, one of them might work, or might not work, or do what was intended. OK, there's another problem with optional. Please look at this. There's a function, give me the value of the optional. And this function is just a member function called value. So if you have a function getString returning an optional string, though there might be a string or might be not, then you can call value, and you get a copy of the contained value. You can assign this value to the underlying object. Value will throw an exception if there is no value. So the code on top is safe. There will be the value in the string, so A will be a string if there is a value, otherwise an exception will be thrown. You should not, if you don't know whether there's a value, just use the star, which you can also use, but the star will not double check whether there's a value, so it requires that there's a value that you know that or that you have checked that. The interesting things are the two lines on the bottom that now R1 and R2. Because you might have the assumption that references extend the lifetime of return values, which in principle is correct. So in principle, you can say whatever get is returned by this function, a reference extends the lifetime of this value, and an optional is a value type. However, we have a problem here. We are not using getString, we are using getStringValue. GetStringValue means getString gives you a temporary object, and value gives you a reference to this object. And then the rule of lifetime extension does no longer apply, because you would extend the lifetime of the reference, not the lifetime of the object this reference refers to. So this would mean that R1 and R2, when you use them, are referring to a deleted optional string. So don't do that. And this, by the way, is a general problem we have in C++. We get more and more reference types with reference semantics and call with reference semantics. We will get more errors like this. You will see in a moment other examples. Here's one example where people might hit this indirectly, without knowing it. A vector of int is returned by a function called getVector. Let's iterate over the int values. So let's do it like this. Oh, it might happen that my vector of int returned is not there. I have no vector of int. So I just switch this code to say, let's call a function getOptionalVector. The return time is an optional vector, and now let's iterate over the values. And this should be safe because value will throw an exception if there is no value. But the problem is this code will iterate over a deleted vector, because internally in the range-based for loop, exactly an auto-ref is used like an R2. So internally, the range-based for loop uses a reference, and it will use this reference to a reference to the return type, so that the return type, the returned object is gone. So this is code that will compile, but you are iterating over a deleted object. Beware of that. That's, by the way, some reason that some companies say the range-based for loop is dangerous. It's a problem of a combination of range-based for loop and applying on the right side something that gives a reference to a returned value. This is not only a problem with optional. Also, if you return, I don't know, a temporary object and like a vector and you use the index operator there, you have the same problem. Then we have string view. This is string view. String view is a new type. It's not a value type. It's more like a pointer type. I would say it's a very dangerous pointer to a character sequence with all the nastiness of a raw pointer, just hidden as a wolf in a string fashion. So it's looking good, but it's very evil. So think about that. If you use string view, it's great, but it looks like you have a string, but you are not only owning the characters below, underneath. So, for example, there's no guarantee that there's a null character. There's no guarantee that if you call data that you don't get the null pointer. A couple of things are different. But it's so nice to use. You can say, well, if I have a function taking a const string by reference, and I pass a string literal, this has a problem that the string literal has to be converted to an std string first. So this is a pretty expensive operation because we copy the values unless the short string optimization is used. Now, if we switch instead to taking a string view, we can even pass it by value because it's cheap. And what we just create as a string view is an object taking the original string literal. And as a string literal exists throughout the whole program, this code is safe. So far, a string view using as a wrapper for a string literal is safe, and we save some computations like allocating memory and compute how long this string literal is, etc., which sometimes can be done at compile time. So we also introduced that we have a conversions from string to string view and from string view to string. String to string view is cheap. We just refer to the characters of a string, and therefore this is an implicit conversion. And you get something like this. So you see that now you have a string view created from the string on the left. But beware, of course, while we have no lifetime problems if we refer to a string literal, if we refer to a string, we have to make sure that the string is still valid. So the first thing is don't use a string view as a return type. So here's an example. Let's concatenate two string views. Let's add them, convert it to a string, and then return the string. This will silently, the result of the plus expression here is an std string, but as we have an implicit conversion to string view, this will silently convert to a string view without a warning in the compiler. So you will not see that you view to an object that is deleted already if you use this. But there are more severe errors possible, and we have seen that already. Here's my favorite example, which I also use to teach the right programming of templates. Assume we have a string view referring to a string literal, which is safe, as we just learned. Assume somebody has to implement an operator plus for a string view the correct way, not returning a string view, returning a string. And that's fine. We have two string views, so we have two views to a string. We concatenate them, so we create a new string, not a view, a real string with data allocated to it, and we return it as a string. That's safe code. That's a safe function. Now let's assume in the same program somebody wrote a cool template. The cool template is, let's compute the sum of two t's, a function template. And of course, the result is a t. So if I add two int, I get an int. If I get two, I don't know, other complex values, I get a complex values. So he wrote this template not thinking very carefully about what he does or she does. Now let's call this. Let's call sum for these two string, for this string view, and passing it twice. You see the problem? What is the problem? We compile this function template where we deduce t to be a string view. That means the return type is string view. That means that internally the plus operator creates a string, but what we return is a view to this internally created string. And at the moment we leave this function, this object is gone, so that we return a view to some data, some character sequence that's not there anymore. And the moment you use this, you run into a runtime error. Again, if you're lucky, you get a caught up. Okay? So that's the danger with string view. Be very careful about that. And by the way, who made a mistake here? How can we fix this? How should we fix this? Template specialization, yeah, that's something for experts, but it's easier. No, second parameter, no? Return auto, yes. Auto solves the problem. Don't do that. Don't return a t. Return auto. The compiler does better know than you what is returned here in the type system, and it does return the right type. So if you learned the return type auto and you learned don't use it, no, that's not the rule for templates. If you use templates, do it, because the compiler knows better what the return type is, at least if you don't directly return the t as it is. So if you return some expression, to avoid some traps, it's usually better to return auto instead of some template parameter t, although this might make your code less readable. But less readable is better than behaving erroneous. So it also internally, of course, I shouldn't use a t here. I have the same problem. So also inside this generic code, I should use an auto, and then this code is safe. OK. Some aspects of this. First of all, you might say, I have already code that uses a const string reference, so let's overload it with string view. You run immediately in problems because this is ambiguous if you pass a string literal. So you might need more overloads just for string literals. And we have that in the standard. The C++17 standard has a problem with all these declarations. They run into this problem. This is fixed in the meantime. We added more overloads there, and this is fixed. So this was ambiguous formally according to C++17 standard. But this will now compile. So a few topics left. Parallel STL. So I run algorithms in parallel. This is an example I like. So I have accumulates values. The problem is it guarantees to accumulate from left to right, which is not very helpful for parallel algorithms. So how should we proceed here? How should we make it better? Well, we can't restrict algorithms as they work. So we introduced a new algorithm, said there's reduce, and with reduce you can say, let's using multiple threads, so let's run this in parallel. So let's in parallel accumulate the values and look at the accumulation. The accumulation just takes the existing value and adds the square of the next value. So we would have to say we start with 0 plus the square of 1 plus the square of 2 plus the square of 3 plus the square of 4. That sequence should accumulate to 30, and if we have 10 of them, that should be 300, the return value, and we get that. If we call accumulate with 40 elements, we get 300, and if we take reduce, we get also 300 as output value. Let's extend this test case to 1,000 elements. Surprisingly, accumulating the same way all the values is giving you 30,000 as a result for accumulating the elements here, and reduce also gives you the same result. Let's step to 1 million elements. So at 1 million elements, accumulate gives you 30 million, and reduce gives you, oh. What's the problem here? And why do we get it now? Looks like overflow. No, it's not an overflow. I use long, long. Long, long can hold 30 million as a value. So what's wrong here? Well, we made an error, but we didn't see the error before. Because now accumulate guarantees to apply the predicate or the function, the operation, from left to right. But if we use multiple threads, we have a problem. Think about taking the last two numbers and applying our function, which means we add 3 plus the square of 4, which is 16 plus 3, which is 17. And then we go further to the left and say, and now let's add 2 to it. So let's add 2 with the result of 3 accumulated with 4. What happens is we compute the square of 4 again. Because the problem is this is not a commutative expression. So the order in which we apply this to a sequence of values matters. Now the question is, why do we see this problem just with 1 million elements? Why don't we see this problem with 10,000 elements or 1,000 elements? And the answer is that in the parallel algorithm world, the implementers can decide what they do. They don't have to compute things in parallel. Parallel is only a hint saying, hey, you are allowed to compute this in parallel. And this implementation, where I found this problem, this was Visual C++, they have implemented that to some extent of values, to some number of values, they still run in parallel, only using one thread. So they did the same as accumulate, but the moment I had enough elements, they started to use multiple threads. So multiple threads might, and problems due to multiple threads and concurrency and undefined order there might just occur if you have enough elements. So beware. Beware, and in your test cases, please use a lot of numbers. And if you use the test cases, if it's just 1,000 values, it's not a proof that it's correct. Okay, what should you do, by the way? That's exactly why we standardize transform reduce, which is because we have to split two things. We have to split to compute in parallel, to compute the square of each value, and then using multiple threads to add the resulting values. And that's exactly why we have transform reduce. This will be the most important parallel STL algorithm we will have, like map reduce. So it will just map the values, transfer the values to some other value, and then combine them in some fashion. So last topic, I think, file system library. We adopted Poo's file system. Here's an example. Let's initialize a path, check is it a regular file, then use the file size or print the file size. Let's iterate over the elements in the directory. If it's a directory, and then otherwise check whether it exists. This code will compile as it did with Boost, Boost file system or with the experimental version of the standard. But there's a surprise. So if you run this in a Unix system, the output is this. So if I pass the root directory as argument, I would iterate over the directories of the root. So if I run this under Windows, you get this. If I pass C:\\, which is what happened here. The Boost file, the file system library already in Boost have this feature that when you print a path, it is quoted, print quoted, and that means it has double quotes around, and each backslash is escaped, which is a nightmare for Windows, because on Windows this looks very strange. So we didn't fix that. We found that to be a huge problem too late. So that's now in the standard. So what you should do is, please, if you print a path and you want to do it portable, call path.string to print it out as a string, and you get one backslash for the Windows version. By the way, can we do this a little bit better? Yes. This will perform multiple operating system calls. Is regular file, is this operating system calls, is directory, exists as an operating system call. That's something you should avoid. We have other options for that. So for example, there's a switch statement, and you can ask for the status and of the path, and then you can ask for the type of this path, and then you have just in the switch statement, you switch between the different options. And by the way, here you see the, not just the convention, but you see here, no, where is it? No, missed. Okay, so what I wanted to say, this switch statement is a new switch statement taking an initialization and then doing the switch. So we have this new if switch statement with initialization here. Good. For those who come from Boost, or for those who come from the experimental implementation of file system, in the standard we changed some semantics. Please beware. Here is a program that shows the difference. If I call this program for user home nico.git, for example, in the past we defined that .git is not a file name, it's a name of the extension of a file name, so the extension part of a file. We fixed that with C++17 when we adopted this to our to the C++ standard, and also as a consequence you could write loops here while we have a file name, remove the file name, and remove the file name and suddenly even remove the slash, so you could iterate over the path elements backwards with programming a loop. This has both changed. So .git is now a file name, not an extension. It's a file name without an extension, and the loop will no longer be used here. It works more the way things should use in self-explanatory. So the point is, if you just switch your old code to this new code, please beware that just changing the namespace and recompiling it might change your behavior. So we fixed some things. Good. That's it. Let's see. Last example. I have a map. I have a map mapping values to strings. And I initialize this map with some customers. What is the problem here? Well, if you have this map, each map element allocates memory, and each memory is allocated somewhere in your program, somewhere in your memory. So if you run this program with some extra statements, you might find out that the elements themselves, the key value pairs of a map belong to a string, are distributed all over your memory, which is a problem if you use cache lines and you want to cache all this data and you want to have it locally located together. For that, we have a new feature called polymorphic memory resources. So just by saying I have a memory pool, you can say I have a pool of values, so I'm pooling new memory the moment I need it, and suddenly your elements are located together in your memory, roughly together. So why is this an issue? Here's an interesting move. I create an std string, but in my map, there is called a PMR string, so that the string also uses this local memory and is not distributed over memory again. And just to make sure, this move becomes a full copy because we are using a different memory pool. So if you have strings now and you move them around and you move them to some other string type that uses this approach of memory allocation, please beware that your moves become strings, and that might be counterproductive though for the whole optimization, because suddenly this code will allocate memory each time we emplace this string. The fix, of course, is that we should already declare S to be a PMR string. Okay, that's it. I ran out of time. I have 2 or 3 others, but that's fine. So that's the traps I wanted to show you. Did somebody learn here something? Okay, so it was helpful. So this is, at the end, my advertisement. We have cool new stuff in the C++17 library. Some people complain that it's not very bringing us forward. It's a mixture of a lot of new things. All things are a little bit small features, not big features, being revolutionary, but applying them together is something that is very cool. But we have traps. And you have seen almost all of them. Oh, no, the biggest one I have. If you want to read more, you got for free as a conference attendee this book. Just to explain that, this book is currently still written. It's now has now 380 pages. It's not done yet completely. You will get all updates for free if you download it and you register with yourself with your email address. You will get notifications, or you should follow my Twitter account. And I should also say that when we wrote the new edition of C++ templates and we published it in 1.5 years ago, we already took completely C++ 17 into account. So there are 2 books that cover both of them. And I'm still catching up. I only have 1 year left before I start with the C++ 20 book. This will be bigger. I know that already. Okay, thank you very much. I'm around here the whole day, so give me feedback or ask some questions. We are out of time. So thank you very much, and see you and have a good fun.